Welcome to the tranquil harbor of the starport, where thoughts drift away from the mundane and float with the starlight. Tonight, our journey will transcend individual stars to explore the true islands of the cosmos, galaxies. As our eyes adjust to the darkness, the ribbon of the Milky Way spans the sky, merely the fence of our own backyard. Beyond the telescope's field of view lies the boundless cosmic ocean, dotted with hundreds of billions of such stellar islands. Let us relax and begin this journey through time and space, allowing the grand narrative of galaxies to soothe our souls. To the naked eye, the stars in the night sky are almost all residents of the Milky Way. But in a few inconspicuous corners, scattered are some faint, persistent patches of light. These patches are not as sharp as stars, nor do they wander like planets. They simply hang there quietly, like faint ink dots on the cosmic canvas. Early astronomers called them nebulae, meaning cosmic clouds or dust. For centuries, humanity knew nothing of their true nature. Philosopher Immanuel Kant proposed a bold hypothesis. He suggested these nebulae might be distant, independent universes, vast stellar systems akin to our own Milky Way. Yet he inadvertently left a precious treasure trove for future astronomical research. His catalog laid the foundation for systematic study of these elusive objects. Sir William Herschel conducted systematic sky surveys. Using his large reflecting telescope, he discovered thousands of nebulae, and believed many were resolvable stellar systems. Herschel speculated the universe contained vast independent stellar collections, yet remained uncertain of their distances and nature. As telescope technology advanced, debate over nebulae's nature intensified. One camp maintained that all nebulae were gas clouds within the Milky Way, while the other firmly believed they were distant, independent galaxies. This marked the famous Great Debate in the history of astronomy. The core issue lay in how to measure cosmic distances, without knowing the distances to celestial objects. Their true identities and sizes remained unknowable. The crucial breakthrough came from a special type of variable star, Cepheid variables, whose brightness fluctuates periodically over time. American astronomer Henrietta Leavitt discovered a precise relationship between their light variation cycles and intrinsic luminosity. This made Cepheid variables the cosmic standard candles. By measuring their light variation cycles and apparent brightness, astronomers could calculate their precise distances. This discovery provided a crucial cosmic ruler for measuring the universe. Edwin Hubble, using the Hooker telescope, then the world's largest, turned his gaze toward the Andromeda Nebula. Through patient observation, he successfully identified multiple Cepheid variables within M31 and calculated their distances using Leavitt's formula. The results were astonishing. The Andromeda Nebula's distance far exceeded the known scale of the Milky Way. It was undeniably an independent stellar system, an island universe far beyond our own Milky Way. Hubble's discovery was published in 1925. It fundamentally rewrote humanity's understanding of the cosmos. The Milky Way was demoted from the center of the universe to just one ordinary member among countless galaxies. Our universe became more vast and rich than ever imagined. Based on observations of additional nebulae, Hubble began systematically classifying galaxies. He proposed the famous Hubble sequence, which primarily divides galaxies into three major categories: elliptical galaxies, spiral galaxies, and irregular galaxies. This classification not only describes the shape of galaxies, but also hints at their possible evolutionary paths. The Hubble sequence remains the fundamental framework for galactic morphology research to this day. From a vague patch of light to a confirmed cosmic island, humanity's view of the universe has made a great leap. We are no longer confined by the Milky Way's boundaries, but now possess a vista gazing upon the boundless sea of stars. Every contemplation of the night sky is a silent tribute to this history of exploration. After confirming galaxies as the fundamental units of the cosmos, astronomers began systematically examining these distant islands. They soon discovered galaxies are not uniform, but exhibit astonishing diversity. Much like Earth's living creatures, galaxies possess distinct forms and characteristics. Edwin Hubble's classification sequence provided the first key to understanding this cosmic tapestry, known as the Hubble tuning fork diagram for its shape. This sequence categorizes galaxies into three primary types: elliptical galaxies, spiral galaxies, and irregular galaxies. Elliptical galaxies are the universe's oldest and most steadfast inhabitants. Their appearance typically reveals perfect ellipses or circles, lacking distinct internal structures, resembling diffuse clouds of light. These galaxies are primarily composed of old stars, where star formation has long since ceased. Their colors lean toward red or yellow, hallmarks of stellar senescence. Elliptical galaxies vary greatly in scale. Giant ellipticals may host trillions of stars, while dwarf ellipticals might contain only millions. They are not significantly brighter than a large globular cluster. Such galaxies typically reside in the core regions of galaxy clusters. They grow by devouring other galaxies. Spiral galaxies represent the most aesthetically pleasing forms in the cosmos. Our Milky Way and the Andromeda Galaxy are classic examples. They possess a bright central bulge and graceful spiral arms curling outward from the bulge. The spiral arms are the most active regions of the galaxy, packed with bright, young blue stars, and vast molecular clouds and nebulae where new stars form. Spiral arms aren't steady streams of stars, but manifestations of density waves. Like traffic jams on a highway, matter compresses here, triggering starbirth. Based on the bulge's shape and the tightness of the spiral arms, spiral galaxies can be further classified into normal spirals and barred spirals. Normal spiral galaxies feature arms extending directly from the bulge. The openness of these arms is classified as A, B, or C. SAW-type arms are the most tightly wound with the largest bulge, as C-type arms are the most extended with a relatively smaller bulge. Barred spiral galaxies possess a central bar-shaped structure composed of stars. Spiral arms extend outward from both ends of this bar. Similarly, arm openness is distinguished as SBA, SBB, or SBC. The Milky Way is a classic SBC barred spiral galaxy. This massive stellar bar influences the flow of matter within the galaxy. Barred spiral galaxies are extremely common in the universe. Approximately 2/3 of all spiral galaxies possess a bar structure. Irregular galaxies, however, break the symmetry and order of the previous two types. They lack a fixed shape, possessing neither a central bulge nor regular spiral arms. They appear as a seemingly random scattering of stars. These galaxies are typically rich in gas and dust, with highly active star formation. Their blue, young star clusters shine brilliantly within them. Irregular galaxies often form through gravitational interactions, or as a result of close encounters with neighboring galaxies. The Large and Small Magellanic Clouds are the most famous irregular galaxies near the Milky Way. They are gradually being torn apart by the Milky Way's gravitational pull. At the boundary of the Hubble tuning fork diagram, a distinct class of galaxies exists: lenticular galaxies. They possess bright bulges and disk-like structures, yet lack spiral arms, and exhibit little significant star formation, resembling a spiral galaxy that has lost its vitality. Lenticular galaxies are considered transitional forms between spiral and elliptical galaxies. They likely evolved from spirals after depleting their gas or undergoing certain dynamical processes. Galactic morphology is not static. It records a galaxy's evolutionary history and is profoundly shaped by its environment. A spiral galaxy rich in cold gas may undergo rapid gas compression and trigger starbursts. If it merges with another galaxy, subsequent gas depletion could lead to its evolution into a lenticular galaxy, or even eventual absorption by a larger elliptical galaxy, becoming part of it. At the dense centers of galaxy clusters, frequent interactions between galaxies strip away their gas, making it difficult for spiral galaxies to sustain star formation, and gradually transitioning them into smooth elliptical shapes. In the vast, empty regions of the cosmos, isolated galaxies are more likely to preserve their spiral structures, evolving peacefully for billions of years. Observing galactic morphology is fundamental work for astronomers. But classification based solely on the naked eye or optical images has limitations. Dust obscures the true structure of galaxies. Different observational wavelengths reveal different aspects of galaxies. Near-infrared observations can penetrate dust to reveal the distribution of older stars that dominate galactic mass, thereby unveiling their true morphology. The ultraviolet band, sensitive to young, hot stars, clearly delineates star-forming regions, helping us understand a galaxy's vitality. Through combined multi-wavelength observations, we can piece together a more complete portrait of galaxies and comprehend the physical mechanisms behind their shapes, from regular to irregular, from blue to red, from active to dormant. The morphological diversity of galaxies is intrinsically linked to their star formation states, dynamic histories, and surrounding environments. These myriad forms in the cosmos collectively weave an epic tale of cosmic evolution. Each point of light represents a unique universe, possessing its own past, present, and future. When we gaze at a photograph of a galaxy, it's easy to perceive it as a static painting, yet the reality is quite the opposite. A galaxy is a dynamic, vibrant gravitational system. Billions to trillions of stars perform a precise cosmic dance governed by gravity. Galactic dynamics is the science that studies the motion of these stars and dark matter. It reveals how galaxies form and maintain their structure, and the invisible force that governs everything. A seemingly simple phenomenon once deeply puzzled astronomers. According to Kepler's laws, in systems like our solar system, celestial bodies farther from the center should orbit more slowly. Yet observations of spiral galaxy rotation curves yielded the opposite result. Whether located near the inner edge or the outermost rim of the galactic disk, stars maintain nearly constant orbital speeds. This implies that matter in the outer regions of the galactic disk is moving at speeds far exceeding expectations. If a galaxy's mass came solely from visible stars and gas, such high velocities would have long since flung outer material into interstellar space. The only explanation is that galaxies are enveloped by a vast, invisible halo of matter. This substance neither emits nor absorbs electromagnetic radiation. We can only detect its presence through gravitational effects. This is dark matter. Dark matter constitutes the bulk of a galaxy's mass. It provides the galaxy with additional gravitational binding, thus explaining the flat rotation curve. The nature of dark matter remains one of modern physics' greatest mysteries. Yet it is undoubtedly the invisible director of galactic dynamics, shaping the large-scale structure of the universe. The elegant spiral arms of spiral galaxies pose another dynamical puzzle. If spiral arms were structures composed of fixed stars, differential rotation, where inner stars orbit faster than outer ones, would cause arms to vanish quickly due to winding. Yet observations show spiral structures persist. Density wave theory perfectly explains this phenomenon. It posits arms aren't solid material arms, but density wave crests resembling traffic jams. Stars and gas flowing through these crests slow down and compress, triggering massive star formation. Young, bright blue stars are born and shine at the crest of the wave, illuminating the spiral arm's outline. They then fade as they move away from the crest. The spiral arm pattern propagates like a wave across the galactic disk. Its rotational speed can differ from the actual orbital speed of the stars, thereby maintaining the structure's stability and longevity. Galaxies do not create stars at a constant, unchanging pace. They experience periods of activity and dormancy, as if possessing their own heartbeat. The star formation rate serves as a key indicator of a galaxy's vitality. When a galaxy possesses abundant cold atomic gas, gravity causes these gas clouds to collapse, forming new stars. However, newborn stars, especially massive ones, heat and disperse surrounding gas through intense radiation pressure and violent supernova explosions, thereby suppressing the next round of star formation. This self-regulating feedback mechanism causes the star formation process to exhibit periodic pulsations. During violent events like galaxy mergers, gas undergoes extreme compression, triggering starburst phenomena. Star formation rates surge hundreds of times. But such explosive growth is unsustainable. Gas reserves are typically depleted rapidly, prematurely aging the galaxy. In galactic dynamics, the core plays a crucial role. Nearly every massive galaxy harbors a supermassive black hole, with masses reaching millions to billions of solar masses. Though black holes themselves emit no light, when surrounding matter falls toward them, it forms a fiery accretion disk that releases immense energy to create active galactic nuclei. While these energy outputs are transient, they profoundly shape galaxy evolution. Black hole feedback mechanisms can drive powerful outflows, blowing gas out of the galaxy, effectively quenching star formation, and regulating the galaxy's growth. A mysterious symbiotic relationship exists between black holes and their host galaxies. The galaxy provides the black hole with accreting matter, while the black hole regulates the galaxy's evolution through feedback. This coevolutionary relationship tightly links microscopic black hole physics with macroscopic galactic dynamics. Understanding galactic dynamics is deciphering the cosmic poem written by gravity, from stellar orbits around galactic centers to the gravitational potential wells of dark matter halos, from the enduring propagation of spiral arms to the profound influence of central black holes. All these elements compose a grand, dynamic panorama. Galaxies are not static entities, but instead, under gravity's command, perform a meticulously choreographed dance spanning billions of years. Galaxies are not eternal, static entities. They resemble living organisms in the cosmos, undergoing a complete cycle of birth, growth, maturity, and demise. Galactic evolution is a monumental epic spanning billions of years. Its narrative threads woven into their morphological distributions and stellar populations, awaiting our interpretation. In the dark ages following the Big Bang, no luminous objects existed in the cosmos. Only a uniform soup of dark matter and hydrogen-helium atoms. Minuscule quantum fluctuations amplified by cosmic inflation planted the initial seeds for subsequent structure formation. Dark matter, influenced solely by gravity, first began aggregating under gravitational instability, forming the embryonic structure of the large-scale cosmic framework, the cosmic web. These dark matter halos became gravitational traps, drawing in ordinary matter. Approximately 100 to 200 million years after the universe's birth, the first generation of stars ignited within the densest dark matter halos. They are known as population 3 stars. These stars possessed immense mass and short lifespans, forging the first heavy elements in the cosmos within their nuclear fusion furnaces. They ended their lives in the spectacular explosions of supernovae, scattering carbon, oxygen, iron, and other elements into their surroundings, enriching the chemical composition of the interstellar medium. Galaxy mergers and interactions are the primary drivers of galactic evolution. According to current cosmological models, galaxies grow through hierarchical clustering. Small structures form first, then assemble into larger systems through continuous mergers. When two galaxies of comparable mass encounter each other, they engage in a gravitational dance lasting hundreds of millions of years. Intense tidal forces stretch stars and gas into long tidal tails. The most visible signature of galaxy mergers, gas undergoes violent compression during collisions, triggering starburst phenomena, rapidly forming vast numbers of stars. The merger process also efficiently channels gas toward the galactic center, nourishing the supermassive black hole there, temporarily transforming it into a luminous active galactic nucleus. When one galaxy is significantly smaller than the other, galactic cannibalism occurs. The larger galaxy tears apart the smaller one, absorbing its stars and matter, though less violent. This process still significantly alters the larger galaxy's structure, potentially creating ripples across the galactic disk, or leaving remnants of the devoured galaxy's stellar stream in the halo. Starburst galaxies are the most extreme stellar factories in the universe, with star formation rates hundreds of times higher than ordinary galaxies. In the core regions of these galaxies, millions of newborn stars simultaneously shine in dense clusters. Their intense ultraviolet radiation ionizes the surrounding gas, forming brilliant emission nebulae. Starbursts are typically triggered by galaxy mergers or intense gravitational interactions. They consume a galaxy's gas reserves at an astonishing rate, though fleeting on cosmological timescales. They represent a violent yet crucial phase in a galaxy's growth, in stark contrast to the violent starbursts. Many massive galaxies have entered late evolutionary stages, where star formation has ceased. These are termed quenched galaxies. The mechanisms of galaxy quenching represent a frontier in astronomical research. One primary pathway is morphological quenching, Galaxies merge to form massive ellipticals, where high random stellar velocities suppress gas cloud collapse and star formation. Another crucial mechanism is environmental quenching. Within dense environments like galaxy clusters, galaxies plow through the hot intergalactic medium at extreme velocities. Their cold gas is stripped away by this cluster medium, much like a fierce wind extinguishing a torch. This process is termed ramjet stripping. Additionally, intense feedback from active galactic nuclei can blow gas out of galaxies, cutting off the raw material supply for star formation. Our Milky Way and the Andromeda Galaxy are currently on a collision course. This provides us with a unique window to study the future of galaxies. In approximately 4 billion years, these two massive spiral galaxies will make their first close encounter. Over the subsequent billions of years, they will repeatedly pass through each other under the pull of gravity. Tidal forces will distort and eventually destroy the original disk structures of both galaxies. Stars will be flung into vast tidal tails, resembling cosmic ribbons of light. During this period, compressed gas will trigger intense star formation, while the central black holes of both galaxies gradually converge, ultimately merging into a larger black hole. The culmination of this cosmic dance will be the birth of a massive elliptical galaxy, tentatively named the Milky Way Andromeda Galaxy by astronomers. This new galaxy will possess ancient stellar populations and an extremely low star formation rate, emerging as the dominant massive system within the local group. The solar system will likely be ejected onto a new orbit during this process. Yet the vast distances between stars make it highly probable the Sun itself will remain unharmed. Only the future night sky will be utterly transformed. The Milky Way's magnificent band of light will vanish, replaced by brilliant stellar arcs and clusters scattered across the heavens. A galaxy's chemical evolution traces another thread through its life cycle. Each stellar generation synthesizes heavier elements through nuclear fusion and returns them to the interstellar medium at life's end. This gradually increases the metallicity of galactic gas over time. Subsequent stars thus inherit richer elemental content. The existence of our solar system, and all heavy elements on Earth, owes to the contributions of preceding stars. By studying the metallicity of stars of different ages, astronomers can decipher a galaxy's formation history, much like reading tree rings. From the initial collapse of gas clouds within dark matter halos, through growth via mergers and intrinsic evolution, to the cessation of star formation due to various physical processes. The evolutionary journey of galaxies is complex and diverse. Their stories are written in the distribution of stars, in the chemical composition of gas, and in the colors of starlight. Understanding galactic evolution is to trace our origins in the cosmos, and to glimpse that distant, certain future. In the seemingly tranquil depths of the cosmos lie some awe-inspiring celestial objects, whose light traverses billions of light years, with brightness sufficient to outshine hundreds of billions of stars in their host galaxies. These are active galaxies, the most powerful sustained energy sources in the universe. Their energy does not originate from ordinary stellar nuclear fusion, but from an extremely dense region at the galaxy's center, the active galactic nucleus. Quasars represent the most dazzling class of active galactic nuclei. When first discovered in the 1960s, their point-like appearance led astronomers to mistake them for stars within our own Milky Way. Yet spectral analysis revealed a startling truth. These star-like objects possessed enormous redshifts, indicating they were receding from us at immense speeds. Their distance from us is staggering, for such distant yet luminous objects to be observable from Earth. Its intrinsic luminosity must be unimaginably immense. A typical quasar shines as brightly as thousands of Milky Way galaxies combined, yet derives its energy from a region smaller than our solar system. This extreme energy density strongly suggests its core engine is a supermassive black hole violently accreting matter. The accretion disk theory provides a framework for understanding this phenomenon. When matter falls into a black hole's powerful gravitational field, it does not plunge directly into the event horizon. Instead, it forms a swirling disk of hot gas around the black hole. As matter spirals downward within the disk, gravitational potential energy is converted into immense thermal energy, heating the accretion disk to millions of degrees. This generates intense electromagnetic radiation, particularly in the ultraviolet and X-ray bands. This is the source of a quasar's immense luminosity. Radio galaxies represent another significant class of active galaxies. They radiate enormous energy in the radio wavelength range. A defining feature of these galaxies is a pair of massive radio lobes. These lobular structures can extend millions of light-years beyond the galaxy's core, far exceeding the size of the visible galaxy itself. The energy for these radio lobes originates from jets emanating from the galactic core. When matter near the inner edge of the accretion disk is guided by powerful magnetic fields, a portion of this matter is ejected at high speeds along the black hole's rotational axis, forming relativistic jets traveling at near light speeds. After extending to vast distances, the jets interact with the intergalactic medium, converting kinetic energy into radiation to form the immense radio lobes. The jet direction determines the observed morphology. When jets point directly toward Earth, we observe a unique phenomenon known as a blazer. Due to relativistic beam steering effects, jets directed toward us exhibit significantly amplified brightness, exhibiting rapid variability and high polarization. Blazers rank among the most violent variable objects in the universe, with luminosities capable of dramatic shifts within hours or days. Ciphered galaxies represent low-luminosity counterparts to quasars, typically embedded within ordinary spiral galaxies. They feature bright stellar-like nuclei and display intense emission lines of varying widths. Based on emission line width, SCFT galaxies are further classified into Type 1 and Type 2. Type 1 SCFT galaxies possess both broad and narrow lines. Broad lines originate from rapidly moving gas clouds near the black hole, while Type 2 SCFT galaxies exhibit only narrow lines. This is attributed to our line of sight being blocked by a dense gas dust ring, preventing direct observation of the innermost high-velocity broadline region. This observational discrepancy led to the unified model of active galactic nuclei. The unified model posits that different types of active galactic nuclei may fundamentally be the same type of object. Differences in their observed characteristics primarily stem from varying observational perspectives and factors such as the central black hole's mass and accretion rate. In the unified model's framework, the core structure of an active galactic nucleus includes a central supermassive black hole. The innermost layer is a high-temperature accretion disk, surrounded by a faster-moving broadline region. Further out lies the slower-moving narrowline region, at a distance of several light-years from the black hole. A massive gas and dust ring may exist, known as the torus. when our line of sight passes directly through the torus to view the central engine. We observe a quasar or Type 1 Seyfert galaxy. When the torus blocks our line of sight, we can only see the narrow line region through light scattered by the torus, corresponding to a Type 2 Seyfert galaxy. If the jet happens to point directly toward us, we observe a blazar. The life cycle of an active galactic nucleus may be brief. Its intense activity requires a continuous gas supply to sustain it. When galaxy mergers or other processes deliver large amounts of gas to the galactic center, an active galactic nucleus may be ignited. Once the gas in the central region is depleted or blown away, the active galactic nucleus gradually fades, returning to a quiescent state. Thus, every luminous quasar we observe today may fade into obscurity billions of years hence, evolving into an ordinary galaxy like our Milky Way, harboring a dormant black hole. Active galactic nuclei profoundly influence the evolution of their host galaxies. The immense energy and matter they eject can modulate or even halt star formation across the entire galaxy. This process is termed feedback. It links physical processes occurring on the smallest scales at the galaxy's core, with the evolution of the galaxy as a whole on the largest scales. As the brightest beacons in the cosmos, active galaxies not only illuminate the distant frontiers of the observable universe, but also provide unique laboratories for studying processes under extreme physical conditions and the coevolution of galaxies with their central black holes. Galaxies are not solitary drifters in the cosmos. They exist within a highly structured cosmic environment, from intimate binary systems to the grand cosmic web. Galaxy surroundings profoundly shape their formation, evolution, and ultimate fate. Understanding the cosmic ecosystem in which a galaxy resides is a crucial link in unraveling the story of its life. Our Milky Way does not exist in isolation. It belongs to a small cluster of galaxies known as the local group. The local group spans approximately 10 million light-years and contains over 50 known galaxies. The Milky Way and Andromeda are its two dominant members. These two massive spiral galaxies together account for most of the local group's mass. The Triangulum galaxy is the third largest spiral galaxy in the local group, and the most distant object visible to the naked eye. The remaining members are predominantly dwarf elliptical galaxies and irregular galaxies. These dwarf galaxies orbit the Milky Way or Andromeda like satellites. The local group is a classic gravitational binding system. Its member galaxies, influenced by mutual gravitational forces, engage in a slow yet determined cosmic dance. The local group itself is part of a larger structure, the Virgo supercluster. This vast, flattened structure spans approximately 110 million light-years, with its mass center oriented toward the Virgo cluster. The Virgo cluster is the nearest large galaxy cluster to us, containing about 1,300 member galaxies that move within a shared gravitational potential well. Galaxy clusters are the largest self-gravitationally bound systems in the universe, typically containing hundreds to thousands of galaxies. They can be classified into two types: regular and irregular galaxy clusters. Regular galaxy clusters exhibit spherical symmetry and pronounced central concentration. Their member galaxies are predominantly elliptical and lenticular. Irregular galaxy clusters, however, feature loose structures and irregular shapes. They contain a diverse array of galaxy types. Within the cluster, scorching gas permeates the space between galaxies, reaching temperatures of tens of millions to hundreds of millions of degrees. This intergalactic medium is primarily detected through X-ray radiation. Its total mass often exceeds the combined stellar mass of all member galaxies. The presence of this medium prevents cooling gas from entering galaxies. This is one key reason for galaxy quenching in the central regions of clusters. Structures larger than superclusters are cosmic filaments, a core prediction of contemporary cosmological models. Cosmic filaments are dominated by dark matter, exhibiting a complex web-like configuration, where filamentary structures connect massive nodes of matter, at which points lie colossal galaxy clusters, while filaments contain galaxy groups and chains, and between these structures lie vast, nearly empty cosmic voids. The formation of the cosmic web traces back to the early universe, where tiny primordial density fluctuations grew through gravitational instability, as matter flowed from low-density regions to high-density regions. After over 13 billion years of evolution, it formed the large-scale structure we observe today. Within the filamentary structures of the cosmic web, vast quantities of intergalactic medium exist. This matter has never undergone the physical processes within galaxies, retaining its primordial chemical composition. It is less dense than the medium within galaxy clusters, yet remains extremely hot, primarily detected through its absorption effects on the spectra of distant quasars. These absorption lines serve as cosmological thermometers and chemical composition tables, providing unique probes for studying the distribution and state of ordinary matter. Gravitational lensing is a powerful tool for studying the large-scale structure of the universe. According to Einstein's general relativity, massive celestial bodies warp the surrounding space-time, causing passing light rays to bend. When light from distant galaxies traverses foreground cosmic web structures, their images become distorted, magnified, or even split into multiple images. By analyzing these distortions, astronomers can map the distribution of dark matter in the universe, including filamentary structures that emit no visible light. Weak gravitational lensing provides statistical measurements, revealing the cosmic web's framework, while strong gravitational lensing offers unique opportunities to study individual distant galaxies. The density of a galaxy's environment decisively influences its properties and evolution, a phenomenon known as the environment effect. In the dense cores of galaxy clusters, galactic interactions are extremely frequent. Processes like tidal stripping and ram pressure stripping effectively deplete a galaxy's gas reserves, resulting in these regions being dominated by elliptical and lenticular galaxies, which appear reddish and have ceased star formation. In contrast, within low-density regions like cosmic voids, galaxies are predominantly isolated spiral or irregular galaxies. Gas-rich, blue-hued galaxies are actively forming new stars. A galaxy's position within the cosmic web appears linked to the mass of its central black hole. Galaxies residing at the core of massive dark matter halos often host more massive central black holes. This indicates that the growth of galaxies and their black holes is profoundly connected to their cosmic environment. From the intimate merger of two galaxies, to the collective motion of hundreds within a cluster, to the cosmic filaments spanning hundreds of millions of light years, galactic environments shape their past and determine their future. Our Milky Way, as a member of the local group, is flowing within a cosmic filament, alongside its neighbors, toward larger mass centers. This grand cosmic ecosystem, binds every galaxy to the fate of the entire universe. Human understanding of galaxies has always been inextricably linked to advances in observational technology. When we transcend the narrow limits of visible light and open the window to full-spectrum observation, a far more vibrant and dynamic cosmic panorama unfolds before us. Galaxies reveal entirely different appearances across different wavelengths, unveiling the diverse physical processes unfolding within them. Optical telescopes initiated the study of galaxies. In this most familiar wavelength range, we can clearly discern the morphological structures of galaxies, observing the elegant distribution of spiral arms and dense stellar regions. Optical observations enable us to conduct a census of stars within galaxies. By analyzing the spectra of starlight, we can determine a star's temperature, mass, and chemical composition, and thereby infer the galaxy's star formation history and evolutionary stage. However, optical observations have inherent limitations. Interstellar dust strongly absorbs and scatters visible light, acting like cosmic haze that obscures celestial objects behind it, preventing direct observation of dust-obscured regions within galaxies. Radio wave band observations open the first window into the invisible spectrum. At these longer wavelengths, interstellar dust becomes nearly transparent. We can penetrate the dust barrier to directly observe the distribution of cold atomic hydrogen within galaxies. This neutral hydrogen gas emits radiation through its characteristic 21 cm spectral line, enabling us to map the distribution of star-forming material in galaxies. Radio observations also revealed the presence of relativistic electrons in galaxies. When moving within an external magnetic field, these electrons produce synchrotron radiation. This radiation is particularly prominent in the radio wavelength band. This allows us to detect magnetic field structures within galaxies and intergalactic space. Infrared astronomy is crucial for studying galactic dust and star formation. After absorbing ultraviolet and visible light radiation from stars, interstellar dust heats up and re-emits electromagnetic waves in the infrared band. By observing this infrared radiation, we can precisely measure the dust content and temperature within galaxies. More importantly, infrared light can penetrate dust obscuration, allowing us to directly observe star-forming regions shrouded by dust and the obscured active zones at galactic cores. Infrared observatories like the Spitzer Space Telescope and the Herschel Space Observatory have revealed hidden star formation activity within galaxies, unveiling a cosmic landscape distinct from that observed in the optical spectrum. Ultraviolet observations, meanwhile, focus on the youngest and hottest stars within galaxies. Massive stars possess extremely high surface temperatures, with their radiation peaking in the ultraviolet band. Through ultraviolet observations, we can directly track ongoing star formation activity within galaxies. Observations from ultraviolet space telescopes like the Galaxy Evolution Explorer indicate that the universe's star formation rate was significantly higher in the past than it is today, providing crucial clues for understanding galaxy evolution. However, Earth's atmosphere absorbs the vast majority of ultraviolet radiation, making space-based telescopes essential for conducting ultraviolet astronomy. The X-ray band reveals the highest energy physical processes in the universe. In this short wavelength range, we observe superheated gas at temperatures reaching millions of degrees, alongside the intense activity of various compact objects within galaxies. X-ray radiation primarily originates from compact objects in binary systems, supernova remnants, and the extremely hot intergalactic medium within galaxy clusters. Observations from the Chandra X-ray Observatory and XMM Newton satellite reveal the presence of vast hot gas halos surrounding galaxies. The total mass of these gases may be comparable to the combined mass of all stars within the galaxy. This holds significant implications for understanding galactic mass budgets and evolutionary histories. Gamma rays represent the highest energy segment of the electromagnetic spectrum. Within this extreme energy range, we can observe the most violent phenomena in the universe, such as jets from supermassive black holes, gamma ray bursts, and potential signals from dark matter annihilation. Observations from the Fermi Gamma Ray Space Telescope indicate that many active galactic nuclei exhibit extreme brightness in the gamma ray band, with luminosity variations on timescales as short as hours, providing unique insights into physical processes near black holes. The era of multi-messenger astronomy has arrived. We no longer rely solely on photons to study the universe. Gravitational wave detection has opened new avenues for observing the cosmos. When two compact objects, such as black holes or neutron stars, merge, they generate ripples in space-time known as gravitational waves. The successful detection by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked humanity's first observation of a compact object merger in a galaxy via gravitational waves. Neutrinos, as another vital messenger, can escape directly from the most energetic sources in the universe. High-energy neutrinos detected by the IceCube Neutrino Observatory may originate from extreme celestial objects like active galactic nuclei, offering new clues to understanding their particle acceleration mechanisms. By integrating observations across electromagnetic wavelengths with gravitational wave and neutrino detection, we can obtain comprehensive information about the universe. Like blind men feeling an elephant, each observational window reveals a fragment of the truth. Only by integrating them can we assemble a complete cosmic picture. Take galaxies as an example. Optical observations show their stellar distributions. Radio observations reveal their gas content. Infrared observations display dust-obscured regions. X-ray observations detect their hot gas, while gravitational wave detection can study their compact object mergers. In the future, we will possess more powerful observational tools. The James Webb Space Telescope will observe the universe in the near and mid-infrared bands, with unprecedented sensitivity and resolution. It will help us detect the earliest galaxies in the cosmos and study their formation and evolution. The Vera Rubin Observatory will monitor billions of galaxies through time-domain surveys to capture movies of the dynamic universe, rather than static snapshots. The Square Kilometre Array will map the distribution of neutral hydrogen across the universe with astonishing sensitivity in the radio spectrum, revealing the evolutionary journey of galaxies from their infancy to the present day. The Athena X-ray Observatory will precisely measure the properties of hot gases, studying how they influence galactic evolution. These next-generation observatories will work in concert across the entire spectrum from radio to gamma rays, and multi-messenger approaches spanning electromagnetic radiation to gravitational waves and neutrinos, to collectively build a complete understanding of our universe. Each time we open a new observational window, the cosmos unveils fresh surprises, challenging our existing knowledge and propelling astronomy forward. In this era of all-wavelength, multi-messenger observation, our understanding of galaxies is deepening at an unprecedented pace. Every technological breakthrough brings us closer to unraveling the mysteries of the universe. We set out from faint patches of light, journeying through galaxies of diverse forms, witnessing their birth, growth, and ultimate mergers. We explored the intricate dynamic dances within galaxies, felt the invisible yet powerful grip of dark matter. We saw active galactic nuclei illuminating cosmic depths like beacons, and understood how a galaxy's position in the cosmic web determines its fate. This grand cosmic panorama transcends the trivialities of daily life, elevating our vision to scales of billions of light years. In this boundless cosmos, all clamor, all strife, seem utterly insignificant. Galaxies evolve slowly over billions of years, their lifespans so immense that the entire history of human civilization is but a fleeting spark within them. Now, let this cosmic vastness enter your heart. Let the gentle dance of galaxies carry away all your thoughts. Let the rigorous knowledge of morphological classifications and evolutionary paths fade slowly from your conscious awareness, replaced by a direct sense of the universe's tranquil essence. Imagine yourself drifting through intergalactic space, surrounded by warm, dark void. In the distance, galaxies resemble luminous clouds, quietly suspended in the endless night. Their motion is so slow, it's almost imperceptible, like the hour hand of a clock, requiring patience to witness its shift. In this vast cosmos, your existence is a unique and precious miracle. Every atom composing your body was once forged within a star, has traversed interstellar space, has witnessed the universe's long evolution. At this moment, allow yourself to rest peacefully. Let go of the thirst for knowledge. Let go of curiosity about the unknown. Simply exist, like a star among countless galaxies in the cosmos, quietly radiating your own light. Take a deep breath. Feel your body merge with the bed. Let the force supporting you be as invisible yet steadfast as dark matter holding galaxies together. With each inhale, draw in the universe's tranquility. With each exhale, release the day's distractions. Let your heartbeat gradually synchronize with the pulse of the cosmos. Slowly, steadily, eternally, the spiral arms of the Milky Way turn gently. The Andromeda Galaxy draws closer. The universe expands in quiet expansion. And you, at this unique moment, in this unique place, exist peacefully. Let the universe's tranquility fill you. Let starlight's tenderness envelop you. In this boundless darkness, you are not alone. Countless galaxies silently accompany you from afar. Their light, after millions of years of travel, finally arrives at this moment, gently settling upon your eyelids, carrying you into a deep and peaceful dream. There, time and space merge as one. Past and future lose their importance. Only the serenity of the present remains. Only the essence of existence endures. Good night, dear stargazer. May you find the deepest peace in the embrace of the cosmos.